To jest ogarnięte, jak rozmawiać. Powiem taki język, taki
Jak chcesz, jak chcesz być bardziej zmatematyzowaną osobą, no to Jerome działa. Znaczy on to już bardziej supergrawitację robi.
So just before starting again, just to say that I've yet again written D minus 2 where I meant D minus 3. So just as, just to emphasize, F really is mu on D minus 3. So. So all I was trying to illustrate in that first part is that we might imagine that a black hole potentially could be time dependent if we're just looking for some solution that's sort of spherical in nature. But in fact, by looking at the Einstein equations, we see that no, indeed, Schwarzschild or one of the Schwarzschild family is the only solution. I just want to briefly mention, for now, in higher dimension, so this is more just a survey type of thing. The sort of, as I say, Myers and Perry first looked at vacuum solutions. With rotation, but then more generally, Horowitz and Strominger back in 1991 wrote, if you like, what was the sort of first in a whole load of papers and work on solutions in higher dimensions that could be associated to solutions in low energy string gravity. So they were really looking at solutions to a sort of general gravitational action. So when you kind of look at the low energy gravitational action, so again, they were very much focused on 10 dimensions at that point in time, then you find that, make sure these look the same fine, you find that you have a scalar field, which I've already sort of had a couple of questions on. You also have a 2 form, so this H here is dB, where B is a 2 form. This is the Neveu-Schwarz 2 form here. And then depending on the type of string theory you're dealing with, you have a sort of host of different forms. So these could be odd or even P forms. And so what they were doing was trying...
Self-duality conditions?
Sorry?
Do you also have some self-duality conditions for them?
Some what conditions?
Self-duality?
Not at the moment. No, I'm not looking at... so, yeah, no. Okay. Simply, I think that's the quickest way of answering it. So if you were writing the self-dual 5 form in this format, you would have to just put some sort of constraint. But this is just meant to be this indicative of the general type of action that they were looking at. So you can see there's a lot more going on than there was for the Einstein case that I was just talking about. So not only do you have these charges, so you can think of these akin to the Maxwell field, I'll say a few more words, but then you also, it's not really Einstein gravity, it's a sort of Einstein scalar. It's a scalar tensor type of gravity. So to find the solutions, they had to put an ansatz. So they kind of assumed So they assumed that there was this sort of block diagonal nature to the metric. So, I mean, I think that in essence was the contrast to what we were just talking about before the break, is that previously what we were discussing was where you're not making an ansatz. You're trying to find the most general metric which looks like some isolated object. So again, in the break, I was reminded that I'd been much too physicsy in my statement of what I was trying to do. What I was trying to do was to say we're looking for a gravitational solution of something which is localized in space and has this some sort of, well, say localized, it depends on some spatial coordinate and some time coordinate. So here, in order to find these solutions, they started off by saying, well, we're just going to make that assumption that you've got this constant curvature space, which they said further was flat. So that would be a kappa is 0. So that's this r to the 10 minus d. But you've still got this common sort of function multiplying that. And then they did a manipulation and boiled everything down to a sort of bidimensional reduction to some sort of study of black holes in this lower dimensional space with lots of extra fields, which had already been looked at by Gibbons and Maeda. And so they were able to deduce that there were a whole set of black hole metrics. So just to sort of comment, this would be a sort of black hole. And this is the sort of, this part is the extending in extra dimensions. So this is why it's called a black brane, because your object is now not localized in your higher dimensional space. It spreads out, it extends. So the solutions that they found carry charges under these p-form gauge fields. And so here, when you think about what does that mean, carry charges, well, if you have a point particle and it's charged, you can represent that simply as a coupling of the Maxwell gauge field to the world line tangent vector. So that's kind of how you represent a charged particle in relativity. And this corresponds to a solution known as Reissner-Nordström. So our F becomes 1 minus 2gm on R plus a sort of q squared on r squared piece. So we have a non-trivial field around the black hole, and that gives rise to extra terms in the geometry. So what this generalizes to in string theory is that we have extended objects. So this would be like a Q again. Where your P form now couples to extended objects. So a 2 form there, gauge potential would couple to a string. It's got 1 extra spatial dimension. A 3 form gauge potential would couple to a membrane, so with 2 spatial directions, and so on. So And so these P-form gauge fields
In general, those higher branes would be non-dynamic as in string theory, right? So for the string, you would
not
have
necessarily, no.
typical Lagrangian, but for the branes, they would not correspond to anything dynamical.
No, I mean, the exact solutions of Horowitz and Strominger are obviously like flat, but you can make them dynamical. You can start looking at zero modes, so I mean, you know, you can make them shift, yeah. But from the low energy gravity perspective, it does become a bit challenging. So. So just like the Maxwell field has a Maxwell stress tensor, which is a two-form, your general P-form gauge field has a P+1 form gauge field strength. And these here are what we would call electric charges. So we can also have solutions which sort of have a magnetic charge where our field strength is now proportional to the volume form on this sort of transverse space of a sort. Sorry, no, on the, let me show, it's easier to show by. So in 4 dimensions, we can have an electric Maxwell field. So we have, in other words, a radial electric field, which would be, so that's magnetic. So this would be a radial electric field, but we can also have a magnetic charge. F is Q sine theta d theta d phi. So this d theta d phi here, sine theta d theta d phi, is like the area form on the two-sphere, and that's what I mean by that epsilon there. It's something that is surrounding the hole, if you like, in the y space. So the Reissner-Nordström solution can't tell whether you have an electric or a magnetically charged black hole. But that's kind of special in 4 dimensions, and it's really sort of about saying that because the field strength, if you like, is a two-form, these are dual, which means like F magnetic is sort of the Hodge dual of F electric. So you can sort of get magnetic solutions by sort of dualizing some of these electric ones. So these are simple, higher dimensional black hole solutions. And just to give an example, I mean, I'm going to refer you to, there's a lot of literature on these solutions. So this is just an example of a particular solution that Horowitz and Strominger found of a fibrane, which is a magnetically charged solution under that Neveu-Schwarz 2 form. And you sort of see that the charge switches on when this R minus switches on, which also switches the dilaton on. And the extremal solution, which is actually the real Neveu-Schwarz fibrane, has R plus equals R minus. So this typically is sort of corresponding to this folklore that if you get an extremal solution with charge, it tends to be supersymmetric. And of course, that's what you would expect for solutions coming from a supersymmetric string theory. But what you see is that in fact, these are obviously solutions to GR, but in finding them, there's very much this ansatz that's been made. So rather than try and think about what the symmetries of some isolated object might be, here it's about sort of splitting the geometry into two different pieces, one of which is sort of tailored towards looking for the particular type of solution, in this case a magnetic solution, with the two-form field. So that's, I mean, there's a whole slew of them, but they're all, I would say, relatively simple in that there's not a lot going on in the extra dimensions. These are all just translationally invariant. So a lot of symmetry.
So the extra dimension is non-compactified here.
No compactifications.
So I suppose, should we think of Q as more of a charge density, rather than a charge of
I suppose. Yeah, I mean, it's... Yeah, I suppose. Yeah. Yeah. I mean, obviously, once you compactify, then you can start thinking about what is the symmetry group on this bit you're compactifying on, and then you can start playing with that, changing that symmetry group, and then you start getting a lot more complex and interesting types of solutions. So, so I think my favorite is the Klebanov-Strassler throat, where you have all sorts of fluxes and, you know, lots of different symmetries. So that one's, there's a lot more going on in that one. Okay, so I wanted to pick up on that thought about extra fields floating around. It's not my phone. And go back to thinking about our black holes back in 4 dimensions. So I'm going to come back to these later, and not today, but over the next couple of days, because in essence, by making this assumption here with this sort of very simple extension, yes, you can find a solution, but you don't know if that would be the solution that would exist. In other words, you know, is that what would be the final state if you had some sort of collapse process? So let me just go back to 4 dimensions and pick up on this thought about how generic solutions actually are. So this sort of rather imprecise version of the Birkhoff theorem that I discussed is saying that if you have all this symmetry, you only have a single one parameter family of solutions of the vacuum Einstein equations or the lambda Einstein equations, and it's parameterized by something that we associate with mass, that mu parameter, which Myers and Perry related to mass for asymptotic flatness. So if you have a more general solution with rotation, then again, although it's a lot harder to demonstrate, what we kind of, in 4 dimensions, we have only these three parameters, M, Q, and J. So what I'd just like to discuss in the time remaining this morning is what gets called black hole hair. So back in the day when black holes were first being studied, first of all, there were all these uniqueness theorems. So that's in essence saying that these are the only parameters that can characterize a black hole. Then gradually, as people thought more about thermodynamics of black holes, and also as we started to expand our notion of what types of fields there might be, and realized if we're compactifying down from higher dimensions, we're going to have a lot of extra fields. The question of whether these extra fields could give extra quantum numbers to black holes became very much pertinent to sort of questions of thermodynamics. So, you know, the problem is that, I'll just use this abbreviation for black holes. Is that black holes really are the ultimate vacuum cleaner. They don't carry baryon charge. And it seems also that they don't carry scalar charge. So it becomes very hard to see how we can make our black holes more interesting. So I'm going to just give a very loose argument as to why black holes do not carry scalar charge. So here I'm going to take Einstein-Hilbert . So here I'm just going to add a scalar field, and again, it's just a sort of meant to be a heuristic argument, and it's saying, well, if gravity is weak, which it generally is, let's just assume that we have a linearized gravity, so we would find a background solution for the scalar, and then we would kind of do back reaction, which makes sense if you've got electromagnetism. So if we look for a static profile of a scalar field on a black hole, our scalar wave equation has the following form. So if our black hole carried scalar charge, then, you know, at the end of some dynamical process, you would expect that it had settled down to this static case. So this would be a sort of endpoint. For the black hole.
You assume spherical symmetry here.
Yes, I'm just making, this is a heuristic. It's just to, so here my F, this is on the Schwarzschild background. Right, just simple. This is just meant to be a very impressionistic argument, because this, in essence, I'm going through sort of the way this developed. So, so here, if I look at what this wave equation gives me, it tells me So what I'm going to do is just multiply that equation by phi primed and integrate. Oops.
Whether it's prime in this first bracket.
Sorry?
That the first
Yes, no, I've integrated. This would be between r plus and infinity. Yeah. Yeah. And so because you want to have finite energy momentum, it turns out that this first bracket is 0. So that vanishes. And then the second bracket, f primed is positive, phi prime squared is positive, f is positive. So again, the second bracket is greater than or equal to 0 unless phi primed is identically 0. So, you kind of would expect that, I guess, with a massive scalar, but if I set the mass to 0, then it's even more obvious that a massless scalar field cannot carry, the black hole cannot carry scalar charge. So this is sort of, if I look here, yeah, it's kind of that already, the clue to that is already here, because I've only got two parameters in my metric, r plus and r minus. R minus is kind of telling me about Q, the charge of the 2 form, but the scalar doesn't have an extra parameter coming in. So it seems like the scalar is really just being determined by everything else. And so that's all, that, if you like, is the clue that these black holes don't tend to carry an additional scalar charge. So for quite a long time, it was assumed that this meant that your black hole could not carry a long-term, sorry, these, I'm going to have to switch to yellow because they're getting tiny. The black hole could not have any sort of field in the vicinity of the horizon. And that's something that we now know to be untrue. So the only thing that I just want to emphasize before I give a rather niche example of a long-term hair on a black hole is that when people often say, oh, there's hair around a black hole, but what they actually mean is that there is some field in the vicinity of the horizon. hair, in the strict sense, would be extra charge, and quite often there's no extra charge carried by fields in the vicinity of a horizon, but there is nonetheless still a non-trivial field around the horizon. So simple examples are where there are some additional fields in your theory. Your black hole has some charge, be it a sort of electric or some p-form charge, or even rotation, and your field condenses near the event horizon to absorb some of that charge. So, for example, scalar fields around a rotating black hole might actually come out of their vacuum and start to take up some of the angular momentum of the black hole. So that it's like a condensate which is screening part of that charge of the black hole. So most of the examples of fields near an event horizon of a black hole are this screening type. So where they screen a charge of a black hole but don't necessarily carry additional information in and of themselves. So that's just a sort of slightly picky point. But in fact, I think it's one of your colleagues here, Piotr Bizon, was one of the people who was the pioneers in showing that black holes could have fields around the horizon. So I thought I would bring this out since this is a local relativist. And back in the early 90s, he showed that black holes could be colored together with Bartnik and McKinnon. And again, this is where you had Yang-Mills fields around horizon. So these were not stable solutions, but they were solutions to the Einstein-Yang-Mills equations. And so it was an important step forward. Another example of a black hole carrying hair, which is stable, is where black holes can carry a sort of topological defect hair. So I'll just kind of quickly go through this. So this is So this is based on a topological defect solution to the abelian Higgs model, which was discovered by Nielsen and Olson. And in essence, it uses the fact that the abelian Higgs model, which, of course, Higgs predicted his particle from famously back in the early 60s, is really the same, or effectively the same, as the London limit of superconductors. So you would describe a superconductor in very much the same way, and in superconductors you can have magnetic flux going through a superconductor, but it confines to vortices. And so your d phi here is and so this Nielsen-Olson solution is very much just saying, first of all, let's take phi So all I've done here is made the Higgs mechanism explicit by sort of taking out this phase, degree of freedom. And so you see that you induce a mass for the gauge field. So that sort of becomes the Higgs mechanism. Your Higgs is now just the real degree of freedom that's left. And the Niels-Knudsen vortex solution has a solution where P is some P of R d phi, and F is just some F of R, and it looks something like this. So this is F, this is P, and what you have is a solution where your gauge field, dP, looks like P primed dr cross d phi, which is, of course, a magnetic field in the z direction. So it's really, that's this business about the superconductor that confines magnetic flux. So these vortices you can thread with black holes along one of these vortices, which gives you a very explicit hair on the black hole. So you get very much the vortex just going through the black hole. And very roughly, but to a very good approximation, this is your solution around Schwarzschild. So these are very direct fields that are on the horizon. And if you, for example, had a magnetically charged black hole prior to the phase transition where the Higgs field acquires a mass, then once you went through the phase transition and the Higgs became massive, that magnetic black hole could no longer exist because the gauge boson would become massive, and so your flux would have to be confined, something like this. Now, I just wanted to finish off in talking about some exact solutions by discussing a particular exact solution, which we can get to by continuing along this line of thought, which is the C metric. So these, when you couple in gravity, these vortices actually have a gravitational effect because, I mean, they should. They're infinite, right? You wouldn't expect a sort of infinite source of energy momentum to do nothing. And so what is a conical deficit, just to be explicit? It's sort of an obvious thing, but just so we're kind of on the same page. If I write down what looks like flat space, and indeed if alpha is constant, this is completely Riemann flat. If alpha is not 1, we have a conical singularity. So I could define chi, which was alpha phi, and that would be in naught in the range 0 to 2 pi alpha. And then my chi would go something like this. So this would be 2 pi alpha. So that's my chi angle. And you see that what that means is you've cut a little wedge out of space. So this is a deficit angle. And it's related to that alpha. You can also have an excess, but the deficit is kind of a bit more intuitive. And you see, we call it conical because if you were to identify these, which of course you should, because that's chi gets to 2 pi alpha, it's back to 0. This is the geometry that you get. It's just a cone. And all that vortex does is take that cone and smooth out the apex. And so the black hole has a killing vector in the phi direction, and so in essence all you're doing for the black hole is kind of chopping out a little bit of a deficit angle. So the horizon becomes, instead of spherical, it sort of becomes, this is of course a wild exaggeration, comes more like a rugby ball shape. I'm not very good at drawing. So just as a pointer to the literature, it was Ariel, Ford, and Vilenkin who first just wrote down the Schwarzschild black hole with an exact conical deficit. You're sort of thinking about what a cosmic string through black hole might be. And then myself with the Chucaro and Kaiken. We looked at the actual abelian Higgs vortex and demonstrated, I mean, both did it numerically, but that's where that rough analytic form comes from. You can solve the equations of motion provided you imagine the string is thin compared to the black hole. So then you might ask, what happens if you have one of these conical deficits, but what happens when you only have it coming out of one pole or there's an imbalance? And so that's what gets you to the C metric. So I'm going to choose to write it with this extra k so that phi is in 0 to pi. And the C metric was actually first, I believe, first written down by Weil back at, well, more than 100 years ago, where he was classifying solutions. But it was, I think, really just realized what it was physically by Kinnersley and Walker. And then a more up-to-date version of these solutions, Demansky, was sort of the paper by Plebanski and Demiansky. So those are sort of classic references. But here I'm using a particular form.
The bracket ends.
Yeah. There we go. I'm using a particular parameterization due to Hong and Teo just because it's actually a little easier to see where this has come from. So our F, so the classic relativists' C metric is written slightly differently. So you can kind of see, again, how this is very much like what we were finding before, but we've now got an extra piece, which is an extra parameter. And here, this A creeps in, and it adds, you know, an extra degree of freedom with respect to what we would call this theta angle. So the killing vectors here are dt and d phi. And the A is sort of coming along. I've just put for comparison a sort of ADS or DS type of extra piece in F. And the A squared comes in a bit akin to what the cosmological constant does. So if A is 0, you see it reduces to Schwarzschild, and this K would tell you you had a conical deficit. So
Since you mentioned that Bizon is a local
yeah.
person, so actually Bizon is from Krakow, but Demiansky and Plebanski are from Warsaw, and Demiansky is from here in the orbit.
As long as I didn't misspell the name or mispronounce it too badly.
Well, I'm afraid you did, but...
Oh, dear. Oh, well. That's revenge for my name at the beginning. Yeah, so, no, I mean, it's just, this is, I mean, it is an interesting metric, actually, so, yeah. So I'm kind of running out of time. I'm just wondering, I'll shift that to tomorrow. So let me just finish off by focusing on the vacuum solution, very quickly telling you how that ties into a black ring. So for the vacuum solution, what you see, if I set m equal to 0, then it still is not explicitly flat space because I've still got that omega factor. So what I do is I do a coordinate transformation. So one of the things that going to emphasize here is just how much gauge choices matter, and some of these are quite useful to know. So if I do that coordinate transformation, then what I get is flat space. So this is known as Rindler, and it's quite useful if you're sort of playing around with things to do with horizons and information. And Rindler is the space-time of an accelerating observer. And r equals 0 corresponds to zeta squared minus tau squared is 1 over a squared. So in this flat space, this is our observer. So the horizon at f equals 1 over a is just a sort of part, the horizon, the limit for what the observer can see and what the observer can influence. And then just very briefly to signpost what Roberto and Harvey did to get the black ring. If MA is much less than 1, we can still kind of, this coordinate transformation is approximately true. And so we get a sort of picture where the observer is replaced by the black hole, and as we analytically continue across the space-time, you get a pair of black holes. There is a conical deficit that pulls these black holes, accelerates them off to infinity. So this is, again, slightly coordinate choice. And then all the black ring is, sort of, do an analytic continuation. So tau would go to IT, and this hyperboloid becomes circle. So that's now completely Euclidean space. And then really, you kind of, what Emperan and Real did was take a dilatonic C metric and then do analytic continuation. So this here is the ring, and then you kind of add a time-like direction. So that's sort of how the C metric feeds into the black ring solution, which is a 5-dimensional GR solution in 5D, the simple one. So I've overrun a bit, but we had lots of questions. So yeah, tomorrow I'll talk about thermodynamics.